Welcome back. In this lecture, I'm going to give a brief outline of the idea behind quasi-Newton methods. We've given a series of lectures on Newton's method and talked about how dramatically faster its rate of convergence is compared to even the best that we could hope for from gradient descent or accelerated gradient descent. But on the other hand, it is much, much more expensive. And it's much more expensive because of an inverse operation. I'll write down these methods now so we can see them again. But the motivation for quasi-Newton methods is to try to capture the best of both worlds, to try to get this accelerated convergence rate that Newton's method promises, but trying to mitigate, at least to some extent, the cost of Newton's method. So let's briefly look back at what we've seen. So gradient descent, this algorithm tells us that xt plus 1 is equal to xt minus eta. I'll write it in this way just to make the comparison crystal clear, times the identity times the gradient of f of xt. Again, we're always talking about minimizing a convex function f. So this is gradient descent. What does Newton say? Newton says, well, we can do better by replacing this identity matrix by the inverse Hessian. So it says, let's let xt plus 1 equal xt minus a step size. Again, if you look back to our lectures on Newton method, you'll see that I'm simplifying a number of details, how we choose eta, etc. But the key point here is that instead of the identity matrix, Newton's method differs just by putting in the inverse Hessian instead of the identity, and then again it's times the gradient. And Newton's method has much faster convergence than gradient descent, but the cost of computing this inverse Hessian is considerable. So quasi-Newton method, say, here's the general picture is, let's do something similar. Xt plus 1 is equal to xt minus eta, and instead of putting in the identity matrix, let's put in some other matrix here. I'll write it as hk times the gradient of f of xt. So if I were to let hk equal the identity for every k, then this quasi-Newton method would be identical to gradient descent. If hk is equal to, whoops, I don't mean hk, I mean ht. If ht is equal to the inverse Hessian of f evaluated at xt, then I exactly recover Newton's method. But this gives us hope that perhaps there is some intermediate ground. Perhaps I can choose ht equal to something that will give me better convergence than just putting in the identity and getting gradient descent, but on the other hand will be less expensive. So in other words, what I want is we hope for an ht that is more useful, in other words, faster convergence, than just using the identity, that would be gradient descent, but is less expensive to compute than this cubic operation of computing the inverse of the Hessian. So let me just give a simple example here. And then in the next lecture in this series, we're going to talk about probably the most used and most well-known quasi-Newton method called BFGS. But here, let me just give a first idea that would tell us that would give us a hint about what we might hope for. So let's first start with an example by picture. it's always important to be able to go back and forth and link your intuition both to pictures, but also to the specific algebra and analysis. So let's suppose that we're optimizing a function whose level sets look something like this. So what do we observe? Well, first of all, it's a convex function. Level sets are all, and therefore all the level sets are convex. And we see that we have some considerable elongation. And as we've talked about in the context of gradient descent, then later in the context of SVRG, then later in the context of Newton's method, this elongation is always the enemy of gradient descent. It's the enemy because if we're at a point, say like this, what does gradient descent do? It moves in the direction of the negative gradient. The gradient, in this case, points outward, perpendicular to the level set, so therefore gradient descent, again, it's not going to take a big step size, I'm just exaggerating it so you can see the direction. It's going to move like that, and therefore we'll have this is essentially the picture explanation of why we have slow convergence. And we're always comparing this to the setting, the rescaled setting, the perfectly rescaled setting, where the level sets are perfectly spherical. So one thing that we see from this picture is that while we probably need some general rescaling here in order to achieve this, so let me write, this would be the perfect rescaling. Maybe instead we can rescale in a simpler way and capture some, if not all, of the benefit. So you'll notice here that I'm going to draw the main axes in dotted lines of the level sets. They're not actually that different from the coordinate axes. So if I were to only rescale the coordinate axes, then I wouldn't necessarily be able to get something that's perfectly spherical, but maybe I'd be able to get something close. So what I'm trying to say is that in this example, it seems that the elongation, the skewness, is nearly aligned with the coordinate axes. So we might hope that we get most of the benefit of Newton's method just by a transformation H, which doesn't rescale all of space perfectly, but just rescales the coordinate axes. Why would this be a good idea? Or why would it be useful in the context of these two things that we want? These two objectives. One, a more useful transformation than just the identity. Okay, so I hope that much is clear. But why does it also meet two, our point two here, that this might be less expensive? Well, let's flip to the next slide and try to answer that question. So if we are only rescaling the axes, what does this linear transformation look like? Remember, our general linear transformation is y equals ax for A, an n by n symmetric matrix. This is a general rescaling, but if you're happy to just rescale by the coordinate axes, then A is much more restricted. Only rescaling axes means that we can take A to be a diagonal matrix, A11, all the way down to ANN, and zeros everywhere. So what does that mean? That means specifically for our context, for our update, our quasi-Newton update, this is saying that we want xt plus 1 is equal to xt minus a step size times h, t times the gradient of f of xt, where h is diagonal, and this greatly simplifies our computation in two ways. First of all, one natural choice of a diagonal matrix to take would be h equal the inverse of the matrix that has the second derivatives of f along the diagonal, but zeros on the other elements. In other words, h is the inverse of the matrix that's obtained by the Hessian by just taking its diagonal. That would be the second derivative of f with respect to x1, all the way down to the second derivative of f with respect to xn, and zeros everywhere else, inverse. So what does it take to compute the inverse of a diagonal matrix? Well, you can see that you can just do it in linear time, down from essentially cubic time to compute the inverse of a general matrix. And that's because I just go to every single one of the diagonals and just flip it. So I can just do that in one pass. In particular, this is just 1 over d squared f dx1 squared, etc. 1 over d squared f dx1 squared. So I can compute this in linear time. And then also, I can compute the multiplication of h with the gradient again in linear time. For a general matrix, a matrix times vector is going to be about a quadratic operation, but in this case, it's a linear operation. So essentially, this is the same computation as gradient descent. So we've definitely satisfied our second requirement. And flipping back to our picture for a moment, we see that if we are so lucky that we have something like this, then we are also going to be doing something much more useful than the identity. So of course, the natural point is that what if elongation is not well aligned with the axes? With the coordinate axes. So our picture would be something that has elongation along something like this. So we can speculate by looking at the picture, but let's just give a specific example that shows that there is indeed the danger that even though this particular quasi-Newton method that I proposed, this h, is so appealing from a computational perspective, it may not always do very well. So let's consider this situation where the Hessian of f is equal to 1, 0.99, 0.99, and 1. You can see that in this case, it looks exactly, the level sets are going to look exactly like what I drew, but even more pronounced. So it has essentially 100-fold elongation. In fact, you can check that the largest eigenvalue is 1.99 and the smallest eigenvalue is about 0.01. So kappa is approximately 200. Remember, this kappa is my beta over alpha, which governs how slowly gradient descent converges. Well, let's see how much h helps us. So you see, unfortunately, h in this case is the inverse of just taking the diagonals, which is just the identity. So using h in this case, we reduce the gradient descent. So no improvement. So this whole story is not necessarily to sing the praises or to denigrate this poor choice of H. It's not about this. It's more to get us into the spirit of thinking of what's gradient descent versus Newton descent. It's just Newton's method is just gradient descent with the optimal affine transformation. And instead of that, we're thinking, what other affine transformations can we put in there that are less expensive but are also more useful? We're going to next talk about a specific way to compute iteratively HT. And in particular, we're going to talk about the method called BFGS, which has been very popular and widely used. We're going to stop here and pick it up next time.